was. So error last time, we had a lot of review and going over and catching up and trying to get us all comfortable with the way things are stored when you do a Fourier transform, discrete Fourier transform in MATLAB. So this was on the board last time. Things that one always trips over. MATLAB counts from 1. The frequencies count from 0. That you started out with, let's say, in our example plots from a few slides ago, 32 numbers. But by the time you get here, you have 32 complex numbers, which is 64 numbers. Obviously, there have to be redundancies. And we went over all of them, actually twice. One is this entry for frequency 0 only has a real part. There's no sign part at frequency 0. The sign of 0 is 0. As the vector is 0, so it's irrelevant. Similarly, at frequency n over 2, which is at MATLAB position n over 2 plus 1, so position 17 in our 32, that's the frequency that going around the circle goes bing, 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 which is to say the real part goes plus 1, minus 1, plus 1, minus 1. The imaginary part goes 0, 0, 0, 0, 0, therefore is irrelevant, i.e. this guy also is real. And the last redundancy is this one equals this one, this one equals this one, this one equals this one. And when I say equals, I mean equals the complex conjugate. So the real parts are identical, and the imaginary parts are negated. Why? Because let's take in the first one, which is position 2, frequency 1, or position n, meaning frequency n minus 1. Frequency 1 means on the circle you go to the next guy, then you go to the next guy. Frequency n minus 1 means you go all the way around but 1, and then you go all the way around but 2, which is to say these guys are frequencies in opposite directions. You can think of this one as frequency 1, and this one as frequency negative 1, so you get the same exact answer. And the point is that the real part is going both these guys as they go around the circle, but the imaginary part is going up for the first guy, but it's going down for the second guy, which means however this sine wave correlates with your signal, this sine wave correlates it just as much, but with a minus sign. That's why you get a complex conjugate. So this is all stuff that we've said at least twice. I just want to make sure we're all on the same page before we get to the next bits. Okay, so first bit is, okay, so you got this set of complex numbers. What do you do with it if you want to show it to somebody? Now, it has all these redundancies in it, so you don't have to show it all. You could just take this bit and only show that. That's the non-redundant part. Now that bit has real numbers in it and imaginary numbers. It doesn't have imaginary numbers everywhere because these first one and the last one don't have one, but the ones in between do. So you could just show me that bit. And you could show me that bit in a number of different ways. Because what's sitting in any one of these numbers is a plus bi, except for the first and the last, which don't have the b. Okay? So you could show me a. You could show me b. Or you could take a plus bi and convert it to, capital A e to the I phi, meaning you could compute square root of a squared plus b squared, which is the amplitude, and you could compute, well, I won't say arctangent because I want the full 2 pi as an angle, so I'm going to say I tan, what is it, 2 of y comma x? I think that's the MATLAB. Somebody correct me if I'm wrong. It's something that will give you a number between 0 and 2 pi, and that would give you the phi. Okay? There's also calls to do this directly, but I'm just saying the math underlying those calls does this. And so we have 4 different numbers we could plot. And we could plot it on a graph with an axis that goes from 0 to the highest frequency that we've got here, which could be, you could label it n over 2, in which case the units on the x-axis are cycles per signal, number of repeats per the length of your signal. You could change the x-axis in various ways, so let's talk about that in a second. But you could plot any one of these guys up here. You could plot A, you could plot B, you could plot capital A, you could plot phi. Any of those are things that you might want to show your reader. Okay? So suppose you want to just show the raw data. So you want to show A and you want to show B. in some books, there are conventions for this. And some of the slides coming up, I think we use those conventions. So, you know, you might say, okay, here's the real part. I've got this. And here's the imaginary part. I got, you know, this, and I've got this, I got this. So you could show A and B. You could show them both and just indicate which one's which. And it's kind of a strange thing to do, but you can do that. And sometimes when you're just trying to learn the math, as we are doing now, and as I will use this convention a few times in the subsequent hour and a half, you know, that's what you're doing. Just saying, what the hell numbers are in there, please show them to me. It's kind of an interesting thing to do. You know, it's got, you know, it's got some DC, because that's zero frequency. It's got some even bits, some cosine bits. It's got some odd bits, some sine bits, and you're just saying, here's what I got. On the other hand, it's fairly atypical to do that. Sometimes you don't particularly care about phase. Say you're describing a sound, and as we will point out, probably won't get to it today, probably next time, but you know, in hearing, we are pretty much insensitive to phase, in one ear at least. I.e., if you give me a sound, and then give me the same sound except you phase shift some things, I will not notice, except in some very exceptional circumstances. So relative phase between components is not something you typically can perceive. And so maybe we don't care about the phase plot. In which case, maybe instead of this plot, we'll do this plot, where we still show what there was at the DC, but then we got this much power here, and we got this much power here, and we got this much amplitude here. Note I took my negative thing and I made it positive, because I'm taking the length of the vector, and I'm throwing away the fact that this phase here is negative pi, I'm sorry. Take that back. It's 3 pi over 2 sine. Okay, so that has a phase that makes it so that treated as an imaginary number, it's minus b. It's a negative imaginary part, but I'm throwing that away because I'm just giving you the length of the vector. This one has a positive vector over here. This one has a positive vector. Okay, and so this would be amplitude. Okay, and similarly, you could do a plot of phase. And so phase, you know, for example, you might force it to go from 0 to 2 pi. And here it's really easy because we got a bunch of positive cosine bits. Okay, phase here by definition is 0, and this guy was 0, and this guy over here was 0, and this guy is positive sine, so that's pi over 2. That's this guy, and this guy, and this guy is negative sine. So that means that the vector is pointing down, which means the angle is 3 pi over 2. So this one would be right here. So there's a possible plot. And it's showing you the non-redundant parts of your spectrum. Now you could plot from 0 to, you know, from 1 to n, or frequency 0 to n minus 1. And what would that do? Well, you have this symmetry. So if you decided to do that, I'll do that for this one, say. So this right here is n over 2. And way off here, you know, you don't actually have an n in the spectrum, but it'd be the same as 0. And you've got this symmetry where this one is also over here. This one is also over here. They have complex conjugates, but the plot I happen to be making is the amplitude. So if you take a imaginary number that's pointing this way and take its complex conjugate, it's pointing that way, but the length doesn't change, which means I'm just going to take these numbers and flip them and repeat them. So, you know, if you go all the way to n, you repeat the DC, even though that your vector only went up to n minus 1. So if I added a number over here, you could do that if you want, or not. And then I take these numbers and just repeat them. So here's this guy, and then here's this guy, and here's this guy, and here's this guy, and here's this guy. Okay? So that would be, take the vector MATLAB hands you, take it its absolute value, literally call the MATLAB subroutine called abs, which for a complex number gives you the length, and then just say plot. Now if you just say plot, it'll call the first entry 1, and the second entry 2. You don't want to do that, so you have to give it an x-axis. So you could say plot, oh, here, I'll write, stop waving my hands. You could say plot 0 colon n minus 1 FFT of my signal. You could do that. And you would get this graph, except you wouldn't get this thing, because that wouldn't be there. Okay? So that's a possibility. It's kind of weird because, you know, this is not, I mean, yes, it's mathematically frequency n minus 1, but it's a weird way to think about it, since all of this could have been over here, right? Frequency n minus 1 acts like frequency minus 1. Frequency n minus 2 acts like frequency minus 2, and that's kind of a more natural way to think about it. So normally we'd take all this stuff and put it over here for any of these graphs. And so for that, let me put it up here, you would get a graph. That hadn't happened at least once today. It happened early, so it got early. Okay, so now I got an excess that starts at 0, 1, minus 1, goes up to n over 2. You could make it go to minus n over 2, but your raw data won't give you that. So it could be minus n over 2 plus 1. I think, did Arrow talk about this last time, wondering which way MATLAB does it? I can't remember. This is one of the problems with teaching these classes. I also often look at old lectures, so I never remember it's what I saw live or what I saw on the videotape. It's confusing. Anyway, so here's our DC for this guy, right? And then this guy happens at frequencies 1 and minus 1, and this guy happens at frequencies 2 and minus 2. So you get this symmetric thing. I guess I should keep going. Boom, 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 boom. And then there's tall one. Okay? So when we graph a Fourier spectrum that way, again, we're giving extra redundant information, but it's giving a symmetry that we kind of is more natural. That we understand that frequency 1 and frequency minus 1 are going to be the same amplitude. They're just going to be, you know, opposite phase, meaning what was a plus angle for one of on the positive axis will be a negative angle on the other axis. Okay. When you do this for phase, when you get over here, this positive angle will become a negative angle if you plot it that way. But the phase plot can often be a little confusing to interpret. Why? Because the y-axis is an angle. You know, it's the place around the circle, and circles keep going. And you've taken that circle and you've unwrapped it and made it an axis, which means plotting something, you know, down here at, you know, negative pi over 2 is the same as plotting it at 3 pi over 2, as I did right here, right? So the question is, do I put it down here or do I put it up here? It's identical, but the question is, what will make the plot pretty and easy to understand? So imagine that you had a filter with what's called linear phase. This just fell completely apart. These things are really interesting. Suppose you had something that had what's called linear phase, which is to say phase was proportional to frequency. Suppose your filter just happened to do that, or your system happened to do that, or your signal happened to do that, so that phase was proportional to frequency. Well, I hit 2 pi, but I didn't run out of frequencies yet. So do I keep going up, or do I go whoop, and then go up again, and whoop, and go up again? Okay? All those are equivalent, because these are angles. If this is 2 pi, that's the same as 0. So it looks, you know, saying it's linear phase says it goes like this. But when you call some function to do it for you, you're likely going to call, I erased, no I didn't, you're likely to call this to get your phase, which isn't going to have it keep going. It's going to have it jump down and go, and then jump down and go. So if you want it to look pretty like that, you have to take this phase, which is wrapping around the circle, and unwrap it to get it to look like the simple function that it happens to be. That's an unobvious problem. It's called phase unwrapping. And you know, if you're curious about that, you know, there may be a MATLAB thing that tries to do it for you. It's not like there's a right answer. There's just a pretty answer. Okay? So it has no import. You're presenting the same data. You're just presenting it in a way that's a bit more useful. Okay, so that's you know, typical ways to plot it, which is the bottom of this graph. So now let's talk about doing some Fourier transforms. Boom, there we go. All right, so let's clean all this up. And let's, oh, look at that, I put it upside down. All right, so let's do some simple examples and do them in our head. Okay? Clean all this up and start over. So suppose I have And then we're going to have a spectrum, which I'm going to plot what I consider the natural way. So here's 0, here's 1, here's -1, 2, -2, etc. Okay? So, y-axis, here's our signal. Really boring signal. Okay? Don't think, don't do the math. What's the Fourier transform? Where is there energy? Where isn't there? Who said I heard a voice? But
It's the DC.
it's 0. Okay, are you pointing to this 0? Okay, correct. This is a boring signal. It's constant, and it is non-zero, so there is something here. The only thing that will correlate it, that will do a dot product in that matrix, that will give you a non-zero value, is the constant. And the constant is the cosine part right here. So the spectrum will be this. And actually, let's erase this part here. Here's the spectrum. I'll use that lollipop plot. Okay? The spectrum is real. It is at frequency 0. Every other frequency you get nothing, because every other frequency is a cosine or a sine. The real part, the imaginary part. You put a cosine and do a dot product, you get nothing, because it all cancels. You put sorry, my finger just did a sine. You do a cosine of any frequency, you do a dot product, it all cancels. So the rest of the spectrum is 0. Okay? All right? So flat goes to spike. Let's do the opposite. Let's put a spike. So my input is now going to be a spike. And I'll put it at the origin, just to make life simple. Okay? We are going to dot product that with cosines and sines. It is 0 everywhere except right here, at position 0. Which means every sine dotted with this will give you what? 0. Why? Because sine of 0 is 0. No matter what the frequency is. Sine is 0 here. It's the only place you could get a dot product, because this thing's 0 everywhere else. So all the imaginary parts are 0. How about the real parts? For every frequency whatsoever, what is the cosine part going to be independent of frequency? Now let me put the 1 right here just to make it easy. What is cosine at 0 for every frequency? 1. Do I care what it is at any other frequency? No, we're doing a dot product. Every other frequency we're multiplying by zeros, which means it's going to be 1 for frequency 0, for frequency 1, for frequency 15. It's going to be 1. So it's going to be this. Oh, sorry, I've got to use lollipop plots. It's this. Etc. Okay? In theory, that's what it is. So first of all, we saw that flat goes to spike, and now we see that spike goes to flat. The Fourier transform going forward and going backwards are pretty much the same matrix, right? Except for a complex conjugate, but basically the same matrix. So you'll often get this thing that transform pairs, real domain, Fourier domain, when you flip them, other than possible complex conjugates happening, you get the same thing going on, which is kind of interesting. Now, when you do this in MATLAB, this is not exactly what you will get. Why not? The DC only happens here. Every other frequency happens 2 different places. The amount of energy this spike has at DC is the same as the amount of energy it has at every other frequency. But at every other frequency, it's represented in 2 places, which means the DC is going to end up being twice as high. That's just a nicety of the way the math works. We were talking a little bit about last time about how MATLAB doesn't make the matrix all have, it's not orthonormal. The columns are not normalized. They're not length 1. So that when you transform, you don't exactly get what you expect. You get something that's everything's bigger by square root of n. And when you do the inverse transform, it fixes that. Okay, so that's one funny thing that happens. Another funny thing that happens is that if you want to get the same length for every component, this component only happens once. The rest happen twice. And so to represent that you have as much of this sign as the rest, you have to do this funny thing. I'll show how that comes out of the math in the next slide. We'll be there in a minute. Okay, so we've just said flat ends up in spike, and spike ends up in flat. As if there is some preservation of information where if everything is really narrow in this domain, it's got to be wide in the other domain. If it's wide in this domain, it's got to be narrow in the other domain. That's actually a theorem. It relates to Heisenberg uncertainty. So there's an uncertainty theorem that says kind of the width here times the width there, there's a minimum of that. Not that everything achieves that minimum, but if you want it to be small in space, it's going to be spread out in spatial frequency. If you want it to be small in spatial frequency, it's going to have to be spread out in space. And we're going to talk about that as we go. So we've done this one, we've done this one. I'm going to go back to the sinusoid in a second because it's on the next slide. I want to go to this one. So normally our signals are written from 0 to n minus 1, but I want to do the Gaussian, the bell curve. And I'm not going to prove that it has this transform, I'm just going to assert it. So here's a Gaussian. And when I draw it this way, ooh, shit, we don't have a vector over here. This part's got to go over here. It's ugly, but remember, the frequency spectrum, which the vector's here, acts like it repeats and repeats and repeats every time. You only show one bit of it, but it's redundant, it keeps repeating. The Fourier transform also acts like your signal, which you've put here, repeats and repeats and repeats indefinitely. It's periodic in the length of your signal, repeats in the length of your signal. In particular, it also repeats over here. So I can draw the Gaussian as this and then have it come back up. But that's ugly. That's not what you think of it as bell curve. Bell curve, you think of it as this. So I'm drawing it this way, but in your vector, this part's got to be over here. In any case, just what comes out of the math is that this transforms over here to the same thing. This is e to the minus, let's say the x-axis is t squared. If you want to use the usual probability theorem version of 2 sigma squared, where sigma is the width. And so over here, you're going to get something that's like e to the minus, there's some constants missing. I'm not going to do the niceties, omega being the frequency, over 2, but the sigma squared goes up top, let's say. Now, first let's give you an intuition about why this might be true. So if I have a low frequency, and by the way, before we rush to do this, let's figure out whether we're going to have real parts or imaginary parts. I centered this guy on 0. This is what's called an even function. Can't remember where we've been using the words even and odd functions, but I don't know if we ever said it out loud. An even function is one where f of t equals f of negative t. It's symmetric around 0, which this is. An odd function is just the opposite. F of negative f of t equals f of minus t. So where it's positive on this side, it's negative on this side. What are the two obvious exemplars of an even function and an odd function? Okay, so you said sine and cosine, but you have to say it in the opposite order. Cosine's the even one, sine's the odd one. And when you do a Fourier transform, if the function your Fourier transform is even, the only thing that'll correlate it with are the cosines. You try to correlate it with a sine of any frequency, whatever the sine is dotting with on this side, it's dotting, the sine is negative on this side, but it's dotting with the same thing. So stuff on the right and stuff on the left will cancel with sine for an even guy. And cosines will always happily, potentially give you a number. As opposed to, if your function is odd, negative here, positive here, cosines will always cancel, and sines have a chance of giving you some power. So that's just a trick. If your function is even, then its transform will be real. If your function is odd, then its transform will be purely imaginary, including the DC, right? Because if it's odd, it's got positive bits over here and negative bits over here, equal amounts, which means the sum of your signal will be 0. Otherwise stated, it has no DC. Okay? So that's just when we refer to even and odd really matter because they tell you what your transform is going to be. So now let's take this guy. It's only going to be cosines. So here's a cosine of very low frequency. And we're going to do a dot product, and where this is plus, and here, this finally got to minus, this system, this signal that we're dotting it with has no power anymore. So we're going to get a big number. Now let's raise the frequency. And it's still correlating really well, because by the time this goes negative, this signal's got no power left. So where the signal has power, the cosine's really high. Let's raise the frequency a whole bunch. Okay, it's a high frequency cosine. Here's positive number times positive number, where I'm doing a dot product by waving my hands. Here's negative number times positive number. Here's positive number times positive number. Here's negative number times positive number. A lot of cancellations, which is saying as the frequency goes up, the amount of cancellations goes up, which is exactly what I drew here. Okay? So that's just an intuition about the fact that the spectrum of a Gaussian should be low pass, which is what you're seeing here. Here's zero frequency, and as I go in higher and higher frequency, I'm getting less and less power. By the way, I'm using the word power. If you hear the word power in a paper, you don't mean amplitude, which is the y-axis here. You mean the amplitude squared. Okay, so if somebody uses the word power or energy, they're usually talking about amplitude squared. Whether it's auditory stimuli, visual stimuli, whatever, those words tend to imply you're squaring things. But whatever, same thing.
Why are we
Power.
Why would we square things?
Physics. You know, so for example, we're going to talk about sound a whole bunch. I don't think we're going to get into today. You know, I brought my guitar and my flute because eventually I may give you a little demo that has to do with sound. That'll probably be Tuesday. But sound is pressure variations. And energy, literal physics energy, the thing that's got units like ergs or dynes or whatever the hell the energy units are, I don't remember my physics, goes as pressure squared. Just fact. You know, same with, you know, energy, whatever. Okay, so we've got this goes to that. Now, suppose I just change the name of the units on the x-axis. So far I've been using numbers like n, because that's what MATLAB does. But suppose this is actually a signal in time. Okay, so this axis is time. And suppose I, you know, write 0 here and I'm write 1 here and 1 here, and what I mean by this is 1 second. Okay? And so that, you know, for a sine wave that goes from, you know, cosine wave that goes from high to low to high in 1 second, which is 1 cycle per second, I'm already getting some cancellations. So that this axis now given, you know, cycles per second, also written as hertz, it's already dropped by 1. Okay? So now I've changed my axis labels. They're not MATLAB labels. They're actually real signal labels you might actually want to use someday. Okay? So that's, I've got the axis, 1 second, and that's now 1 cycle per second. Okay? But suppose I change the axis label. Just change the units. Okay? Suppose I decide to do everything in milliseconds. So that means this spot here is 1,000 milliseconds. Okay? And now my drop is, you know, it's 1 cycle per second, but per milliseconds, it's 0.001 cycles per millisecond. If I'm changing my units on both of these, so now this is cycles, you would never do this, but cycles per millisecond, cross out hertz. Okay? So this is now in milliseconds, this is now in cycles per millisecond. So this number just multiplied by 1,000. And this number just divided by 1,000. Okay? That's just fact about the units. That's not anything fancy about the math. But what it says is, if you squeeze this guy, you're going to spread this guy out. If you spread this guy out, you're going to squeeze this guy down. Now let's think about this in intuition terms rather than just this silly argument I gave you about units. So I've now messed it up something fierce. You know, this signal, which is a Gaussian, which went to the Gaussian I've got plotted over there. Suppose I actually did squeeze it down. So let's switch colors. Is that going to work? Yeah. So suppose we have a new signal, which is still a Gaussian in form. It's just that sigma got smaller. A lot smaller. Okay? That's my new signal. Now let's correlate that with sine waves, cosines. Okay? Now, this frequency, which is a much higher frequency, correlates it with OK when it didn't correlate with this guy at all. So much higher frequencies still give you a reasonable dot product, which means over here, I can go to much higher frequencies before I drop. Okay, that doesn't look like a Gaussian. Sorry about that. It should. Okay? So I've just squeezed the signal here and just gave you, just by doing the dot product, by with my hand in the air, saying that this guy's going to correlate with much higher frequencies, which means it's going to spread out. So that's what I mean, is that if you squeeze the thing in the signal domain, you effectively stretch it out by exactly the same factor in the Fourier domain. Sigma squared in this spectrum, in this description of my Gaussian, is in the denominator. Sigma squared over here is in the numerator. Okay? So this was a function of t over sigma, and this is a function of omega times sigma. Okay? So when you squeeze here, you stretch there by the same amount. Okay? That is a theorem. I just proved it by waving my hands rather than writing out mathematical steps. But if you just write out what you mean by squeezing and by stretching and write out the definition of the Fourier transform, this will come straight out of it. Okay, let's go to the simple example, and then we'll come back to this list in a second. So what about if I do a sinusoid? So I've got a signal domain over here, and I'm going to have a transform over there. And I want to go back to what you get from MATLAB, so I want to actually label everything correctly. So this will be transform. This is Fourier. Okay, so we got from 0 to n minus 1. We store that. And suppose my signal is a cosine for the moment. Okay? And suppose it's 3 cycles per signal. So it goes down, up, down, up, down, up. Okay? It is a cosine, therefore its transform will be real. It is a perfect cosine in my signal. This, by the way, does not make it all the way up at n minus 1, because where it wants to make it all the way up is here at n, because it repeats. And so for it to be perfectly a cosine, it has to make it most of the way up, just like when we developed the matrix way back when. Okay? So there's my signal. It obviously has content at frequency 3. So over here, I'm going to put 0 in the middle. 1, 2, 3, minus 1, minus 2, minus 3. We've got power here, and we've got power here. And that power is all real because my signal is cosine. Right? And we're getting power at minus 3 because frequency minus 3 cosine and frequency plus 3 cosine are exactly the same thing. So number one, you always have that symmetry. The other thing is cosine, here's a cosine function. If I'm dotting with this, or I'm dotting with this, where this is times 0, time 1, time 2, because I'm going down the signal backwards, you're dotting with exactly the same thing, you get the same answer. And in particular, if the height of this is 1, then you would think the height of this would be 1/2, and you get 2 of them, thus giving you the 1. Again, MATLAB will not do that. It will multiply those numbers by square root of n, where n is the length of your signal. But it will still have these 2 items on either side, and they will be half as high as what you would have gotten if you had the constant function and put it at 0, as we talked about a second ago. Okay, that's if you have a cosine. Suppose instead you have a sine. So now we're starting at 0 and we're going up to 1, down, up, 1, down, and back, up to 1, down, and almost back. Okay? So that's my sine. And it's an odd function, right? Because if I took this bit and put it over here, it's anti-symmetric around 0. Where it's positive on this side, it's negative on this side, and vice versa, which means you'll only get imaginary bits. Okay? And so you'll get, but over here, you got to get the conjugate. So it'll be like this. I'm asserting that, but now let's say y. So I want this spectrum to give me back my signal. So let's see, what's going on here? Okay, so suppose my signal is the cosine, which I did just a second ago. So that's cosine 2 pi times whatever your frequency over n times sample. And all this we can call omega, which is what's on the slide. Okay? So that's just my cosine written down. Now we want to build that by adding complex stuff. And so the question is, how would you do that? Now, we're going to do that out of these basis functions which are in our complex matrix that we've been working with. Okay? And our complex matrix has, frequency e to the I omegas, which is to say cosines plus I sines. So let's look at what that math is trying to tell us there. I can get rid of this stuff here. All right. So suppose I write what's on the right side of the top of that slide. 1/2 e to the I omega n plus e to the minus I omega n. Okay? Well, that looks awfully ugly, so let's write it out. That's 1/2 e to the I omega n is Euler's formula, so it's cosine omega n plus I sine omega n. This is the same thing except negative frequency, plus cosine minus omega n plus I sine of minus omega n. Oops, sorry, cut that off. All right. We have a cosine omega n, we have a cosine minus omega n. Cosine is an even function, which means cosine minus omega n is the same as cosine omega n. So I've got 2 cosine omega n's times 1/2. So we get cosine omega n from the cosines. Now, I have an I sine omega n, and I sine negative omega n. Sine is odd, which means sine of negative omega n is the same as negative sine omega n. This thing is minus I sine omega n. Just this thing by itself. Right here is plus I sine omega n. These guys cancel. Spam call. No, call from home. Okay. So cosines on the opposite sides, you want things to cancel. Sines, if you want to get a sine, you're going to need to do something on the 2 sides of the frequency axis. So let's, again, derive that one. So sine's an odd function. If you wanted to get a real sine omega n, again, you have to play this trick because you're going to have components on either side, and you need those components on the other side. So what do we got here? We've got sine, we've got e to the I omega n minus e to the minus omega n. E to the I omega n minus e to the minus I omega n. Again, write it out. This one is the same as that one. So this is, is cosine plus I times sine, leaving out the argument, so it's the same. And this one, now we're going to take a minus. We have cosine, right? Because cosine of minus omega n is the same as cosine of omega n, so I'm skipping the step that I just used. So this is going to be cosine. And now we've got, this one I'm going to write down because we're going to need it. It's going to be plus I sine negative omega n. Okay? So we got the cosine minus the cosine. They're going to cancel now. I left out the I over 2. Right. Whole thing. Yep. Sorry, all of this times minus I over 2. Okay, so we got cosine minus cosine, that cancels. Now, we have an I sine, and this is the same as minus I sine omega n. So we have I sine omega n minus I sine omega n. So those don't cancel. So we're going to get minus I over 2 times 2 I sine omega n. That's what we got. The 2's cancel. I times I is negative 1, and there's a minus. So minus I squared is 1. We get sine omega n, which is what I asserted. Okay? So this trick in the math is a bit about when you run the Fourier transform, what does the Fourier transform do? It takes these numbers on either side, maybe two real numbers, and it multiplies them by things that look like this to reconstruct your signal. That's what it does when you do the complex inverse Fourier transform. It takes these complex exponentials, multiplies them by your transform, and adds them up. You want to end up with something real by the time you're done. So I've just demonstrated that if you have a spectrum that is real, it will reconstruct and give you a cosine. And then if you have a spectrum that is, well, as drawn here, imaginary, negative imaginary, it will reconstruct to something that's real. This is just another version of the math to say what we've been saying for 2 sessions now. That when you have a real signal, the Fourier spectrum is going to be something on the positive frequency axis and its conjugate on the negative frequency axis in order for this math to give you back a real signal. And this math is doing it one piece of the spectrum at a time. So a real piece of the spectrum will effectively be on both sides, right? You'll have it on plus frequency and minus frequency. And when you reconstruct it, doing the inverse Fourier transform, you'll be multiplying it by things like this. And this math says, ooh, look at that. If I have a real number on both sides, the sine parts cancel, and the cosine parts add and give you back what you want. And then if I have, as we will, if there's any sine component of your signal, you'll have an imaginary part over here and a negative imaginary part over here. It will reconstruct by doing this, which will cancel all the imaginary parts and give you the sine as a real signal, which is what you want. So it's just another way of saying stuff we've said before, which is that this thing reconstructs back to where you started. Real. So the complex math, again, is just a way of hiding the sines and cosines, but it all works out. Okay, so coming back here, that's a sinusoid gives you either real, if it's cosine, imaginary, negative imaginary, if it's sine. If it's something else, meaning if it's phase shifted, you'll still only get stuff at 3 and minus 3, but it won't be all real, it won't be all imaginary. It'll be a complex number, and it'll be complex number here, complex conjugate here, and the complex number you get here, let's say it's A plus BI, here's real, here's imag, here's A, here's B, here's the amplitude of this thing, its length as a complex number, and here is 5. That's the phase shift. Right? That was in the math that we did when we developed the Fourier transform. Right? We kept going from C sub r and S sub r when we developed it, and we converted that to A and phi. I'm just saying that again. Okay? So that if your signal is a sine wave of frequency 3, but not cosine, not sine, but some other phase phi, then you're going to get a complex number here, whose amplitude will be the amplitude of the sine wave you put in, and whose phase will be the phase that you shifted it to. The phase is 0. This will be a number, real, because it's cosine. If the phase is pi over 2, meaning you actually gave me a sine wave, the sine of t, then it'll be a imaginary number, pure. But if you give me in any other phase, you'll get an A plus BI, whose angle will be the phase that you presented me on the input, and whose length will be the amplitude of the sine wave you gave me. Okay? This same Cartesian polar just keeps coming back. It comes back for systems, comes back for Fourier transforms of signals. Okay. 2 other highly relevant in neuroscience signals and their pairs. One is a difference of Gaussians. So suppose we Gaussians. So let me go back to doing Gaussians. And let me go back to acting like we're symmetric around time 0, even though that's not how the math lab works, and we're centered around frequency 0. Here's the Fourier transform. So a little while ago, I had a Gaussian that went to a narrow Gaussian, and I had a Gaussian, let's do it like this, that went to, actually I'm going to make this guy taller. I'll tell you why in a moment. That went to a wider Gaussian. Actually, that moment is now. Notice I put them the same height over here, which means they have the same DC, which means the sum of the signal across all these places has to be the same. So this guy is summing over a lot of places. This guy's summing over very few places. So for the sum to be the same, he's got to be taller. So I'm going to make him taller so his DC is the same. Okay? So suppose I then compute a new signal. So green goes to green with the Fourier transform. Black goes to black with the Fourier transform. Suppose I take green minus black. That gets me a new signal. Right, blue. That's okay. Okay? So this minus this is a number, say, around here. This minus this is a number, say, around here. No, sorry, around here. And eventually the green goes underneath the black, which means green minus black becomes negative. And so I'm going to get something that's going to look, well, here's where it's 0. So I'm going to get something that's like this. Okay? So the blue, this, that's a bad way to write it. So this is green minus black. So how does that transform? The Fourier transform is a matrix multiply, right? Which means the Fourier transform is what? Behaves in what way? That we've been talking about all semester long. It is, fill in the blank. Linear. Which means if we put in A minus B as the input, we get Fourier transform of A minus Fourier transform of B. Because it's just a matrix multiply, so it's got to satisfy everything. So now over here, we're going to get the Fourier transform of A minus the Fourier transform of B. So we took green minus black, so we're going to get a bunch of stuff that's in negative cosine phase, but I'm plotting amplitude, so I might as well take green minus black over here instead of black minus green, which means blue is going to be this minus this. Right here it'll be 0. Right here it's going to be maximal. It'll be symmetric. I didn't draw it symmetric. So the transform of this guy, which is a Gaussian minus another Gaussian, often called a difference of Gaussians, otherwise known as a dog. Woof. So the dog function gets that's Fourier transform, which you would describe how? If it were a filter, say, what would it do? If it were a system, not a signal, if it was something that you put stuff into, if it was the impulse response function of some system, is this blue thing, kick it, you get that out, then the system multiplies the Fourier transform of the input by that blue thing, and so as a filter, it behaves in what way? It is bandpass. Doesn't like low frequencies, doesn't like high frequencies, likes a middle range of frequencies. So it is a bandpass filter. Its Fourier spectrum as a thing is bandpass, meaning its Fourier spectrum is concentrated in a band of frequencies with lower content at lower frequencies and less content at higher frequencies. Okay? And this is often used, for example, in the visual system to model what receptive fields of ganglion cells or LGN cells look like. You can fit them with difference of Gaussian and fit them quite closely. So it's a good example of the way you filter visual input. It doesn't work for auditory input. We're going to get back to that a bit next time. But why would this be a bad impulse response for sound? Why would it be problematic? What's wrong with blue? as a description of something you do to a sound. Note the number 0 is sitting right in the middle of it. What can't you do when the x-axis is time?
You have a constant
It's-
sound, you cannot hear it.
No, that's not
It's
it.
negative.
It goes into negative. You can't go back in time. It would be non-causal. Okay? When you do something in time and you kick it, when you want to describe a system that you actually could build in reality, when you kick it, you cannot get an impulse response that goes into the past. And if you can, please tell me about it. We'll all get rich. Okay? You can't do that. So that, a difference of Gaussians, for example, is not something you would typically use to model a physical system. Now, on the other hand, and by the way, I wrote the spectrum over there, and I wrote it all with solid lines. The spectrum is all real, right? Because this guy's even. Okay? Now, suppose you're not modeling a system you can actually build, but rather, you have some data, EEG data, neural data, whatever, fMRI data, MEG data, and you want to take that data and you're particularly interested in a range of frequencies. And you want to say, how does that range of frequencies change over time? I want to filter it in some way where I'm preserving only those frequencies. Now, if you built a causal filter, then what that means is every time you detected a good bit of content, your output would appear later. But you don't want to say that. You want to analyze your signal saying, right now, there's a lot of 300 hertz. And I want to say that, which means I want to use a filter that is even. I can't build it and actually run it real time because it needs to have an impulse response that goes negative. But if I collected the data, and then I want to process my data to reject some frequencies and include some frequencies, I don't want to shift the content around in time because I care about when it happened. Okay? So you might actually use this in data analysis. We wouldn't use it to model a real system. But to analyze data, you want to do this. So this is a system, if you think of this as an impulse response, this is a system where all the phase shifts are equal to what? What number? It's all solid over there, no dashed lines. So all the phase shifts are 5, 3, 12. It's all cosine parts, it's even. Phase shifts are all 0, right? If you plot the phase, they're all cosine, there's no signs in there. Every phase shift is 0, which means no signals get delayed or advanced. That's what you mean by a phase shift is 0. So you refer to this, if you want to talk about it as a filter, as a 0-phase filter. So you can't build those in time as actual systems which run real time, because they're not causal. But you can use it for data analysis for a signal you've already collected, which you want to analyze, and when you find frequency content that you're interested in, you want to say, here's where that frequency content was, not it happened 10 milliseconds later if it was 100 hertz, and it happened 5 milliseconds later if it was 200 hertz. That would be bad. You're shifting things around, and you're shifting different frequencies by different amounts. You don't want to do that. You want to say, at this time, this signal had this. Whether that signal is brain data, auditory data, analyzing speech, whatever it is, or even visual data, MRI. You got some content that was highly wiggly at this place in the brain. You don't want it to get shifted off to the right just because you decided to look for fast, spatially fast modulations. You want to place it where you found it. So for analysis, you can build non-causal filters and really mean to do that. In fact, it's typical what you would do. Not just sensory data. Not everybody here is interested in sensory stuff. We've got people interested in other aspects of human behavior. So another place it comes up. I do motor stuff in my lab. I have people do reaches and I track their fingers, and so I have data that are kinematic. So it's overt behavior, motion. Eye movement data. Suppose you want to know what the eye's doing as somebody's looking at something. So that's X or Y as a function of time. With an arm, X, Y, and Z as a function of time. So you get these functions of time, which are kinematics of a moving limb. And if you want to filter that data because your device that's collecting the data is a little noisy, and so the track looks kind of like this, even though it was a nice smooth movement, and And so you want to get rid of that high frequency bouncing around. You want to filter it out. But you want zero phase because you don't want to move the kinematics to somewhere else. You want to center it on where your best estimate of where it was. Okay? So, phase matters, but you got to think about what phase you meant if you're generating Fourier transforms, because you're using this as an analysis tool rather than you're just running FFT on something you've collected. Okay, the last one is the Gabor. So the Gabor is a good one to talk about because it uses some aspects of the Fourier transform that are worth pointing out that we haven't pointed out yet. So if we have a signal, A, and it Fourier transforms to A tilde, and we have a signal B, and it Fourier transforms to B tilde. If we take A plus B, we get linear. Okay, so we get A tilde plus B tilde. I've already used that, and that was how I got the difference of Gaussians. If I take A convolved with B, and I do the Fourier transform, what do I get over here?
A tilde times.
Say it again?
A tilde times.
Okay, we've got to say what we mean by times. So what we mean by times is each frequency component of A and the corresponding frequency component of B get multiplied. If you do it in MATLAB and it's complex numbers, it's a complex multiplication, but still multiplied, sure. But if you're going to do that in MATLAB, where A is a vector and B is a vector, you would not say A dot B. MATLAB would complain. You just gave me two vectors and said multiply them. I don't know how to do that, right? So you would have to either say A tilde transpose times B. That would be one MATLAB way to do it. Or you could say dot of A tilde and B tilde. You could do that. Or you could say A tilde dot star B tilde. These are all sort of MATLAB-y ways to do what Asen was just trying to say. Okay? So we have convolve becomes pointwise multiply. Now, the Fourier transform is just this matrix multiply. The inverse Fourier transform is kind of the same matrix multiply. There's a conjugate in there, but otherwise it's kind of the same thing. Which means that it satisfies the same thing. What transforms to A tilde convolved with B tilde? Answer, A dot, in the sense we just meant, B. So if you convolve here, you pointwise multiply there. If you pointwise multiply here, you convolve there. And this is just because the Fourier transform had, the inverse Fourier transform, convolve, acts a bit like the Fourier transform. Other than that complex conjugate, it's kind of acting the same way. Now, I'm going to assert this, and I'm going to use it. I'm not going to prove it. But it's going to be really important for the stuff we're going to do today. We're going to use it a lot. Okay? So this was just the convolution theorem which we used to understand why Fourier transforms were useful. Because this is a really expensive thing to do, and it's kind of hard to understand what it does. But we can take our signals, go to the Fourier transform, just say, oh, it's a filter. It just filters each frequency independently. That's dot star. And then I can go back. That was that big diagram we said about what Fourier transforms do. But it also works in reverse. So how would I use this? Well, first time we're going to use this is by talking about what a Gabor function is. So here's a Gaussian, and it transforms to, so this is 0, and this is Fourier transform, and it transforms to some other Gaussian. This is a sine wave. All right, keep the same height. And it transforms to this plus this. This is 0. We've already done that one. I'm using a cosine, it doesn't matter that I'm using a cosine. Let me finish this example, I'll take a pause.
The products that you drew on the board before, you drew two dot products or two inner products and had one pointwise multiplication. So those wouldn't all be equivalent.
Oh, shoot.
Only the last
Why did I do that?
Only the last one.
That was just totally wrong. Let me say that out loud. You just pointwise multiply, you don't sum. Never mind. When I wrote A tilde transpose B, that was just wrong. That gives you a number, not a vector. When I wrote dot of this, that gives you a number. Ignore that. Sorry about that. The last one, dot star, is what I meant. Went off the rails there. Okay, so this transforms to this. We've talked about this today. This transforms to this. We've talked about this way. Now I'm going to do a dot star over here. All right? I'm going to just take, at each time, this times that. And what that gives you, when this is high, it gives you my cosine wave. And as this goes low, my cosine wave gets smaller and smaller. Okay? So that's called a Gabor function. Gabor is probably how it should have been pronounced. The guy's Hungarian. And Gabor function has some interesting properties. One, we talked about how big you are in space, how spread out you are, and how spread you are in the spectrum, and that the product of those has a minimum that it can achieve. The Gaussian achieves that minimum. The width of this times the width of this is as small as you could possibly get in a pair, where width is in the sense of variance, never mind how I'm measuring width. But there is this product that has this minimum. There's a theorem about that. Turns out this guy also satisfies it. So it is localized in space, right, because it gets smaller and it doesn't go out forever. And it turns out it's also localized in frequency. Now, how do we do its transform without ever doing any of the math? And just do it by looking at it. Learning these theorems that we've talked about, notably this one, and the scaling stretching theorem, those allow you to think about your stimuli and think about what spectra are and what they will do without ever doing the math, and without even bothering with MATLAB. So, for example, what do we got here? This is this dot star that, which means the Fourier transform of this, Fourier transform of this, is this convolved with this. This is just two spikes. This is a little Gaussian. How do you do convolution? You take this guy and you roll it across and you multiply and add. Now multiply and add is particularly easy because this thing's zero almost everywhere. So you only get something when the Gaussian runs into it. And what do? You get a copy of your Gaussian. And then you get nothing. And then you get a copy of your Gaussian again. So the spectrum is going to look like this. This is zero. This is nicely lined up with that. This is nicely lined up with that. You're going to get a little Gaussian on the positive frequency side and another one on the negative frequency side. Okay? We just did a Fourier transform in our heads. This is a useful thing to be able to do, to intuit about your signals and your systems without bothering to do the math. Here's our Fourier spectrum. Again, what word would we use to describe this? Same one we used for the dog. It's bandpass. Doesn't have low frequencies, likes mids, doesn't like highs. Let's look at this guy. Of course that's true. What correlates well with this? A frequency that looks like the frequency you built it out of. And when the frequency gets higher, you get cancellations. And when the frequency is lower, you also get cancellations. Okay? So just looking at this, this obviously has a preferred frequency. This is also a model that we use in neuroscience all the time to describe what cells are doing. Typically, we're now not talking about the retina if you're in the visual domain, we're talking about V1. So a V1 receptive field is typically described using a Gabor function. And that can match simple cell receptive fields in V1 very, very well. And can match what they look like when you measure them in spots of light, which you can do with V1 simple cells, and can match what happens if you show them sine waves over here. Okay, so those are just some very useful transforms using these very simple rules. If I take a Gabor function and squeeze it, meaning I take a narrower window and I take a narrower, meaning a higher frequency sine wave, if I totally squeeze it, then I take this and I stretch it, which is to say I move it to preferring higher frequencies. But we can intuit about more complicated things to that. Suppose I leave the window alone. Okay? And because if I take the whole thing and squeeze it, this is all going to stretch, which means these guys are going to move to higher frequency and they're going to get wider. Okay? Both of those things will happen. But suppose I left this guy alone and just made the frequency higher, which means in the same window, which is the Gaussian above, I now put a higher frequency. So I got more wiggles. And I fit more wiggles before it died out. So that would convolve this with these guys being at higher frequency, which means they'd be just as wide, but they'd be over here. So the point is, main point is, that once you know these rules, you forget about all the complicated math, you can intuit a good bit about how systems will behave, how signals transforms will look. You may want to design a stimulus based on having a particular frequency content. And this allows you to think about how you would do that without necessarily doing all the math or just playing in MATLAB. Okay, now let's take a break. Take 5. Back to it.
Lab is a tutorial.
Yeah.
Wait, so we have lab and then the tutorial after?
No, it'll be
Or
like,
the
I'll
lab
do
is
it all
the
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 lab
way.
is a tutorial.
Yeah,
Okay.
yeah.
Okay, so, what's all this stuff for? So, you can use it to talk about signals, you can use it to analyze signals, you can use it to talk about and analyze systems. Analyzing a periodic signal. So if you have a signal and it repeats and it repeats and it repeats, so that the discrete Fourier transform makes sense, you take one repeat and you analyze it, you say, here's what the frequency content is. Obvious example, which we'll get to, but at the rate I'm going, definitely next time, a week from today, is analyzing sounds. Analyzing auditory stimuli and talking about the content of the auditory stimuli and talking about auditory processing systems like your stereo, your phone, your ear, your inner ear, etc. All of those which process signals in and produce signals out can be analyzed with this math. Designing the system. So if you want a system to do, so I've alluded to this already, if you want to design a system that is shift invariant to analyze signals and you want it to behave in a particular way, this math is useful. So as I said, there are systems that you want to analyze which are existing systems. So you're interested in how a ganglion cell processes temporal modulations of visual inputs. You have an input that's flickering over time, and you're looking at the signal coming out of the ganglion cell, which is modulating over time. You ask, is the ganglion cell acting like a linear shift invariant system? Well, shift invariant, I hope so. In the small, meaning if you deliver that signal later, you should get the same answer. But not all aspects of physiological systems are shift invariant. For example, systems adapt. So if you give it a signal and then test it with a signal a little bit later, versus you don't give it the first signal and you test it later, if the first signal adapts it and desensitizes it, then the response to the second stimulus will be weaker following the first one than if it was presented alone. So that's basically a failure of linearity, but it's also kind of a failure of shift invariance in the sense that the system is now in a new state. It's not the system has a clock in it, and it knows that it's 5 o'clock and it's going to behave differently. Shift invariance really means no matter when you hit it, it'll behave the same way. But nevertheless, the system has some memory, and some memory that acts in a nonlinear way. So physiological systems don't follow all this math, but you can restrict yourself to a set of stimuli where it does obey the math pretty well and learn a lot about the system that way. Arrow gave that same spiel a week ago, as I recall. Or maybe it was Tuesday. If it's Tuesday, this must be evening. But you also sometimes are designing a system. So we alluded to that in, I want to analyze my data. So if I want to analyze my data, and I'd like to look at certain aspects of my data, like these frequencies versus those frequencies. So in EEG data, one often talks about the power in different frequency bands. The alpha band, the gamma band, the beta band. These are ways of analyzing EEG, saying certain frequencies represent different things, they represent different neural signals, I'd like to analyze them separately. Which means you want to take the raw EEG that came out, which is just a signal that's sampled, so many times per second, digital signal that we usually work with, but then you want to filter it and say, okay, here's what I'm considering the alpha power, here's what I'm considering the low gamma power, the high gamma power, the beta power. So those are different frequency bands, which means you design filters that are meant to take that part of the frequency band and erase the rest. So in particular, you're thinking about this as a linear shift invariant system that now is being used to analyze a signal. It's not, you don't build it, you just use it on your computer to analyze a signal that came out of your experiment. And you are imposing a null space, meaning those signals which don't get through my filter. So if I want a high gamma band thing, somebody can remind me of where the high gamma band is, I don't know, 10 to 16 hertz? I don't remember. It's some frequency band. If you want that, what you're saying is you want the null space to include all the frequencies above that and all the frequencies below that, and so you want to design a filter which only includes those. Okay? And if you're going to design that to analyze data while the participant from whom you got the EEG was doing something, then when an event happens in high, whatever, high gamma band, and you get some power there, you'd want it to be said, I had that power at this time while the observer was doing this, or maybe 200 milliseconds after the stimulus was shown, or maybe 50 milliseconds before they got around to pushing the button. And so you may want to correlate activity with overt behavior, which means when you measure it, you want to attribute that stuff to a time, which means you don't want to delay it in time by right of the signal processing you did, which means you might want to use a zero-phase filter, a filter that doesn't delay the content by right of being causal. If you wanted to build the filter out of parts, then you couldn't do that. But if you collect the signal later on want to analyze it, then you might, in fact, intentionally use a zero-phase filter. So when you read about, in papers, about people doing signal analysis, be that EPG, MEG, or kinematics of movement or whatever, you will often see the phrase zero-phase filter. Because what they're telling you is that they were careful when they analyzed the signal looking for when does this particular frequency band have power. They want to attribute it to the right time. They don't want to arbitrarily shift it in phase, meaning in time, because phase for a temporal signal is a shift in time. Okay, so that's the kind of thing that we want to do with these tools. So examples of that, analyzing systems. So here are two Gaussians, meaning the difference of Gaussians filters that we talked about. On the below is if you take this minus this as a signal, so something that looks like that, and you take its Fourier transform, you get something that looks like this. Now this does not look exactly like the difference of Gaussians that you might have expected to see here. Why does this one look funny? It doesn't look quite like what I drew before, which was just take this Gaussian and subtract this other Gaussian. Why does it look like this funny shape? Because it's in logs. Because very often when we analyze systems, they have a really big dynamic range, and so plotting it logarithmically allows us to see more of the action. And often in frequency space, especially in temporal frequency space, log makes more sense. Temporal frequency space, why log makes more sense, meaning talking about the auditory system, is something I'll get to next week. Not this time at the rate I'm going. And so what you see on the right are neurons. Each one of these is an individual neuron from the back of the eye, so the output of the optic nerve, and you're listening to a single neuron while you're putting sine waves on the screen. So the sine waves are literally bright, dark, bright, dark, bright, dark. So it's just a visual pattern being presented to the animal while you listen to what a ganglion cell is saying, and then you vary the frequency in cycles per millimeter across the screen, although here put in the units that we usually use, which is I want to know what the frequency is at the back of the eye, and so I talk about for each degree in angle leaving the eye, how many cycles fit in there. Okay? And so your thumb at arm's length is about 2 degrees wide. Obviously, this differs amongst the thumbs in this room, so it's just a approximate. But so when I say 2 cycles per degree, that would be 4 little black stripes and 4 little white stripes painted on your thumbnail held out this far. Give you a feel for what the units are. Okay? And so these are neurons that are cutting off at about 2 cycles per degree. This one's a little higher than 2. This one's a little lower than 2. This one's a little higher than 3. And that also cut off at the low spatial frequencies, and the dots are measurements, and the solid lines are a fit of the difference of Gaussian's model. So it says that the standard model that you've seen for what neurons in the back of the eye look like, if you've ever seen this in a perception class or an intro neuroscience class, they usually say this neuron is excited by light here and inhibited by light surrounding it, often referred to as lateral inhibition. And if you put a sine wave grading over it, bright strip here, dark strip here, bright strip here, that'll correlate really well. But if it goes bright, dark, bright, dark, bright, dark here, and you're looking cancellations here, you won't get an output. And if the bars of the grading are really wide, so this is the bright strip and the dark strip's way over here, you're exciting it and inhibiting it at the same time, and so you also get cancellations. So the frequency it likes to see is one where this is the bright part, and this is the dark part. Of course, I drew that backwards, but you know what I mean. Okay? And so that's what you're seeing. You're seeing a bandpass filter, which has a frequency that it most prefers, which is determined by the size of the center, the size of the plus part, and that the inhibitory parts lead to a drop-off in the low frequencies, and a drop-off in the high frequencies is because the center is so big that it's pooling over a big region, and if you go bright, dark, bright, dark, bright, dark over that region, you get cancellations. Okay? So this is one example of just using this math in a useful way to describe a system that we have in hand. Okay. Now, at all times we're talking, when we actually run this stuff, about doing the discrete Fourier transform, the one you actually do in MATLAB, the one where you give me samples of my signal at discrete points in time. I should go your way. Okay? What's the value of my signal at time 0, at time 1, at time 2, at time 0, 1/40,000th of a second later, 1/44,000th of a second later, 1/44,000th of a second later. Why am I saying 1/44,000th? Because that's what the device in your pocket does when you get an MP3. Okay? So all the signal processing stuff is useful everywhere. It's useful in engineering, signal analysis, understanding systems. It's useful. It's just ridiculously useful in math. But one place it's really useful is storing auditory signals, like on your phone. Okay? So auditory signals, in most of the standard store a signal methods, are sampling at a fixed rate. And the fixed rate for recorded music, I don't know if anybody buys CDs anymore, but on CDs or in MP3s that you download, are at 44 kilohertz. Okay? 44,100 maybe is the number. I don't remember what number industry decided on, but they decided on a particular sampling frequency. Now, why would they sample at that frequency? So first of all, let's intuit it before we go to the slide. So suppose I'm sampling a signal. Got green. What happened to my black? That's what happened to my black. Okay. So we are sampling in time. This is time now, and there's a sample at time 0, and time index 1 and time index 2, where this index is 1/44,000th of a second. Okay? Now, before we get into the math, what is the highest frequency sine wave that I could possibly catch if this is how often I'm sampling it? Well, might be high here. It's eventually going to go low, but I have to notice that it went low, and the next time I can notice it went low is here. And then it goes high, and then in sample 3, it goes low. Boom, 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 boom. Any frequency higher than that's going to not get caught accurately. Something's going to happen. We're going to talk about what happens. But already, this frequency in the Fourier transform is sitting where? When you do FFT in MATLAB, where is this frequency going to be? In the output. So if I have n samples, and so I run FFT and I get this vector of n, where is this frequency? The one that goes up, down, up, down, up, down. It's at n/2. And it's the one where we get the real part, but we don't get an imaginary part, because the imaginary part would have been 0, 0, 0, 0. So it's the highest frequency that the Fourier transform can possibly give us. Okay? So if you sample a signal, the signal in the world played by whatever instrument is producing this sound is not, discontinuous. The sample in the world is this. It's a continuous thing, but you're only noticing its values at discrete points in time. And so by sampling at 44,000 hertz, you're saying that I cannot represent any frequencies higher than 22,000 hertz. Interesting choice they made. None of you can hear 22,000 hertz. You guys, if I played it right now, can probably hear 18,000 if I push it loud enough. And I won't hear that anymore either, because presbycusis, the aging of the auditory system, is such that you lose high frequencies with time. And so I cut off around 13 or 14,000 right now, and that's why teenagers can get these cell phone rings that they can hear and their parents can't. You just put it at the right sweet spot. And by the way, you cut off at 17 or 18 now. When you were 5, you went up to 19 or 20. So it's already happened to you. You just haven't noticed. It's just happening more to me. Anyway, okay, so now let's talk about what sampling does and, its importance. So suppose I play a frequency that's too damn high. So here's one that, so let's see where it is. Not nice, get someplace where it's nicely lined up. Okay? So this frequency is going down and right back up, not down to the next sample and up to the next sample, but it's going down and up in one sample's time. That's way too high, right? And it's a frequency that's going down and almost all the way back up, but not quite. So this was frequency n over 2. This one is frequency n over 2 in indexing terms, but once you get the time axis in it, it's in frequency. So here's a sampling rate, which is 44,000 samples per second. That's my sampling rate. And this frequency is, so let's call this, I don't know if I've got any notation coming up, but let's call this the rate of sampling. And this frequency is R over 2 hertz. Okay? This frequency here is almost R, meaning one cycle is happening in just longer than one sample. So the frequency is just lower than one cycle per sample, just a little bit slower. And look what happens. So we're sampling at time 0, time 1, times 2, and these are the samples I get, the black dots. Which is to say a frequency that's almost R, just under R, is looking like a really low frequency. Because this really low frequency would give you exactly the same samples. Which means this really high frequency and this really low frequency, once you sample, you can't tell apart. Go back to trichromacy, metamers, right? This system, which takes a continuous signal but only measures it every once in a while, signals that in that every once in a while have the same value, you can't tell them apart. If it's this value here, and then it does all kinds of crazy stuff in between, and then goes here, and then does all kinds of crazy stuff in between, and then lands here, that signal and this nice smooth signal, as far as this systems are concerned, are identical. Can't tell them apart, because you're only measuring it at these discrete times. Now, doing all kinds of crazy stuff in between means an extremely high frequency, because it's doing a lot of wiggles in an incredibly brief period of time. So all these high frequencies can alias down, look like lower frequencies. Now we noticed this before when we defined the Fourier transform itself. I don't have the axis up anymore, but the discrete Fourier transform went from 0 to n over 2, and then up, and by the time we got to n minus 1, this frequency, which is really high, looked like frequency 1. It was identical. I mean, other than the opposite sine phase, it was identical. This is the same math, just now we're analyzing continuous signals and sampling them, but it's the same idea. So the idea is that one frequency can masquerade as another. Okay, what does he want me to do in terms of the math? I don't really need to because we've already done it. It says that when you have this frequency that's going around the circle this fast, and then you sample it, it'll look the same. So if we put up our circle, use our discrete samples in time for one round of the thing. So if we have one, cycle, if we go around this circle, this to here, then to here in the next sample, then to here in this sample, okay? So that's one cycle per signal. If we instead go all the way around and then one more, it'd be identical, okay? So that's one cycle per sample, which is to say, it's just way the hell higher frequency. So the point is, if by the time we do our sine wave, we land in the same exact spot as if we'd only gone by one, those frequencies look absolutely identical. If we go all the way up to here, which is the same as just going up by 2, frequency of n equals 2 on our plot, those would be identical, okay? If we go all the way around, but just one short, that's still too damn high. Because what I've told you is the highest frequency you can really represent is rate over 2. That's the one where I go from here to here to here to here. That's the +1, -1, +1, -1 in the Fourier transform. Okay, that's the n over 2. If we go to n over 2 plus 1, it means we're going all the way to here and here, which is the same as going this way to here, which means that the n over 2 plus 1 masquerades as n over 2 minus 1. The n over 2 plus 2 masquerades as n over 2 minus 2. The n minus 1 masquerades as doing 1. Okay? Other than the sign flip, but that's neither here nor there. That's just the amplitude. Okay? So that's the aliasing phenomenon. And if you just write down the math, what you're saying is, and I think Arrow did this at some point. Yeah, I think he did this last time. Is that the sine, 2 pi frequency. So I'll call it, f over n times n. That's fine. But if I now go sine 2 pi f plus n, for example, over n times n. So I've gone to a much higher frequency. In there is 2 pi f over n plus 2 pi n over n, which is 2 pi. Okay? And that, so we got sine a plus b, which we can do some trig formula for. But in that trig formula is sine 2 pi times an integer. And sine of 2 pi times an integer is 0, no matter what the integer is. Which is to say, this and this are going to be equal. You go one spot, or you go around the circle in one spot, they're going to be equal. And so you have this problem that sampling has things masquerading as other things. So how does that work, and how do you fix it? So imagine I've got some signal, and I do its Fourier transform, and it's that. Now I'm going to sample the signal. So now the dance I'm doing right now is we've had a whole week and a half or whatever of talking about this discrete Fourier transform. One slide said, oh, there's lots of kinds of transforms. There's transforms for discrete math. There's transforms for continuous math. There's transforms for finite signals that repeat, and there's transforms for infinite signals. So I'm going to dance around that and say, all the math we've talked about and all the intuitions that we've talked about how transforms work for all those other Fourier transforms. So I'm going to move to the continuous domain, even though we've never done the continuous math in this class. All right. So we have some continuous signal, whatever it is. It's not on the board, but it has that Fourier spectrum. But I'm going to, make up some continuous signal and assert that its Fourier transform is what you got there. I'll attempt to draw this thing. Wiggle, 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 wiggle. 0. Okay, so that's that transform, absolute x of omega, and this is, x of t over here. Now, this is music, and this is its Fourier transform. Now we're going to take the music and make a CD, which means we're going to sample it. Okay? So I'm going to have a new signal in time, which is a sampling function, which is these are all equally far apart. Right. And this is the time difference between one sample and the next, I'm going to call delta. And this is just another function of time, which means it has a Fourier transform. And let's assert that this is time 0 right here, which makes this an even function, because it's the same to the right as it is to the left, which means when I do a Fourier transform, I'm going to get real stuff, not imaginary stuff. Only cosines will work. And what's it going to possibly correlate with, dot product with? Well, one obvious thing that it correlates with is this cosine. Down, up, down, up, down, up, down, up. Okay, there's a frequency that seems to work. If you do a dot product, you can get a nice positive number. Obviously, if you go out to infinity, you get an infinite number, but we're not going to deal with the issues of that. What other frequency will be high by the next one? So let's say this guy frequency is, so this is delta, so this is 1 cycle per delta. 1 cycle per delta seconds is the frequency I just drew, which means the frequency is 1 over delta. So if delta is a 44,000th of a second, the sampling rate is 44,000 hertz. I'm sampling 44,000 times per second. Okay? That's all the 1 over delta is. Now, what other frequency will correlate with my little sampling function? My sampling function are infinitely narrow things with height 1 happening every 44,000th of a second. Okay? What other sine wave could I have drawn there that will be at a peak at the next, that's at a peak at 0 and will also be a peak at a 44,000th of a second? What can I do to the frequency to make it so that it matches? First, think about higher frequencies. How much higher do I have to get so that it's going to peak at the next guy?
2 times.
I got to double it. So I got to go down, up, down, up. So the first up is against 0, but the next up is sitting right where there's a guy. Which means it'll always, every time there's a peak, it'll be up. And so when you do a dot product, you're going to get a number. If you do any frequency in between there, sometimes it's going to be up, sometimes it's going to be down. You're going to get infinite cancellations, you'll get nothing. So in other words, the spectrum of this has, let's call this the sampling rate, R. So the green one, sorry, I should do that in green because the green one is R. So you're going to get R, but the spectrum is going to have R and 2R and 3R, go up, down, up, down, up, down, up 3 times, and 4R, etc. Yeah?
Can you just repeat? So we had the piece like sound and you sampled it?
We haven't done the sampling part yet, but we're about to.
So what are the bars again?
This is our sound.
Okay.
This is going to be something I'm going to multiply by our sound, which will just pick off its values at discrete places and delete them everywhere else. I'm about to do a dot star. Okay, so I'm about to multiply
it.
it.
To do the sampling.
Huh?
It's what we're going to use.
What we're going to use to do the sampling. It is called a sampling function. Okay, or a sampling grid, if you will. Okay, and I want to know the Fourier spectrum of the sampling grid. And the Fourier spectrum, I've just told you, is, well, it's got some DC, because its average value is non-zero. And then the next frequency that happens is at R, minus R. And the next frequency that happens is at 2R, minus 2R. And the next frequency that happens is at 3R, etc. In other words, this funny cone function over here, its transform is a cone function. Now this is a transform pair, and I'm giving you intuition why it has to look like this. It also satisfies the scaling theorem we talked about, which means if I sample more frequently, these other guys are going to get pushed out. If I sample less frequently, these guys are going to come in. Okay? Now, my sampled function down here is this dot star this, meaning where I want a sample, I take a sample. Where I don't take a sample, I've got nothing. Here I take another sample. Then in between them, I get nothing. And then I take another sample, and then I get nothing. And then I take another. So you get this function that looks like, I'll draw it up here. It looks like this. That's what you get when you sample it. You get the samples, and you don't get anything in between. And we have a theorem for that. And the theorem for that says, if I do dot star here, I do convolve over there. And convolve with little spikes, we've already done, we did it for the Gabor. It just means you take your signal and you put a copy of it at each spike and you add them together. That's what this is showing you. So if my sampling is at these frequencies, so the 2 pi, I do 2 pi every delta seconds. So the frequency is 2 pi per delta if you want to do it in radians per second. That's what the x-axis label. It's in a different units than I had over there, but it's the same idea. And so my spectrum of the sampling grid is a spike here, a spike here, a spike here, and then repeating spikes further out. Okay? And my spectrum of the sampled thing, my spectrum of this thing, dot, 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 without all the curves in between, it's dot star over here, so it's convolve over here, which means take a copy of this, put it here, another copy, put it here, another copy, put it here, and because those copies overlap, they'll add. And so I'll get a copy here, but I'll get a copy here, and look, oh my God, down here at low frequencies, I'm getting what was high frequencies. Does that sound familiar? Here's a high frequency in the signal, but when I sample it, that high frequency is showing up at a really low frequency. That's aliasing. That's exactly what I meant by aliasing. High frequency stuff masquerades after sampling like low frequency stuff. I showed it to you for a sine wave by itself, but if I have a signal that's got a lot of sine waves in it, this sine wave sampled this often masquerades as this low frequency sine wave. This is 0 right here. Okay? So that is aliasing done in the math, but now using the Fourier theorems that I showed you earlier in the day, where if you are multiplying in the time domain, you are convolving in the temporal frequency domain. So this is kind of bad, because I want to sample my music and have it sound like my music. But if my music has some crazy, ridiculously high frequency content in it, then all of a sudden it's going to sound like something audible. You know, frequencies that are as high as R look like 0. So something as high as R minus 400 will sound like 400 hertz, which is, something you can hear. And it's something you don't want to hear because that wasn't in the signal. It was way the hell up here where you couldn't even hear it. So that's bad. So how do you fix that? And that notion of high frequencies masquerade as low frequencies happens every time we sample. Another place that we sample is images, right? Because we never have continuous images except when we look at the actual world. But we spend a lot of time in front of these screens that have pixels. And the pixels only happen in certain places, which means someone pointed a camera at the world, looking at a continuous thing, but then sampled it in particular places at so many, it's no longer samples per second, it's samples per degree, or samples per inch, or samples per meter. It's sampling. Except now it's sampling this way and this way. And what it says is if you don't sample enough, things will look funny. So for example, I take this picture, and I just throw away 3/4 of the pixel. I take every other pixel this way, every other pixel this way. If this image has some high frequency stuff in it, now all of a sudden it's going to masquerade as low frequencies. So this is that image, literally throwing away 3/4 of the pixels. So just taking every other pixel in this going up and plotting, putting it here, and every other pixel this way, and putting it here. And look at these stripes. Sometimes we call that moiré. So I was using the example of going to the beach. If you go to the beach where there are dunes they're protecting, so they put up those little picket fences in front of them to hold the dunes together. And if there are ever two fences in front of each other, and you look through one at the other, you see stuff like this. Why? Because the picket fence in front is sampling the picket fence behind. And their frequencies at your eye are not identical because the other one's further away, but they're comparable, which is to say that the second one's frequency frequency is too damn high for the sampling the front one's doing, and so its high frequencies are masquerading as low frequencies. So we call those moire. Okay? It's even more interesting with the fences. How many of you have actually experienced this particular thing? Nobody?
Not with fences, but.
But yeah. I'll tell you when you experience this, if you ever watch television. TV cameras sample. People wear clothing. Sometimes they wear clothing that's too damn high frequency. A tie with the stripes, or a suit with, checks that are way too high. And when the guy moves around, all of a sudden you see these low frequency stripes that look awful. You would think the industry would pre-filter. I'm going to tell you what pre-filtering is in a second, and get rid of this problem. But they don't. What they usually do is just instruct people, don't wear clothing like that. But when they have an interview subject, they can't do it. And so often when you're watching the news, I'm glued to MSNBC far too often, and people come up for interviews and they're wearing the wrong kind of clothing for current day cameras, because the current day cameras, for some reason, even though this one's probably smart enough to do better, do this stupid thing, which is they allow aliasing to happen. Now, how do you fix that problem? So suppose I'm going to sample at delta, which means delta over 2 is the highest frequency that doesn't alias, and if I go any higher, I'm starting to alias. So why not take the spectrum and delete the stuff I can't represent, otherwise known as pre-filter. Put it through a bandpass filter. You could just cut off at n over 2, but such filters behave badly, so usually we smooth out the sides a little bit. Plus, they're easier to build that way anyway. And so we built some low-pass filter. This is the zero frequencies. We're passing low frequencies. We're deleting high frequencies. So we design a filter. This is, again, using your math for a useful purpose. To take my signal, low-pass filter it before I sample it. So this would be, in the image domain, literally blur the picture before you get to the CCD camera. Don't have to blur it a lot. Just blur the ridiculously high frequencies that your sampling is not going to be able to handle anyway. So a tiny bit of blur. And a good camera will literally have something in there to do that. So before you sample it, you low-pass filter it. So now here's your spectrum, this thing. And when you sample it, now you get these replicas, but they don't overlap. They're way up here in the high frequencies. So now this is the spectrum of your sampled signal. When you play it back and send it to a video monitor, you just get rid of these. You either get rid of them because you filter them again, or you get rid of them because your monitor can't handle this high stuff anyway. And so you don't see it. Okay? And so if you do that here, so here's those stripes. But if I take this guy right here and I blur it, okay? So I literally convolve it with a Gaussian or some other filter that's low pass, such that the frequencies above this sampling frequency, which is every other pixel, are now gone. So I blur this ever so slightly, then do the every other pixel thing. Then when you do that, they go away. Okay? So this is pre-filter and then downsample. Downsampling being take every other pixel. That's downsampling by a factor of 2 in x and y, a factor of 4 in the total amount of data you have. Okay? So anytime that you want to do sampling, anytime you have a physical system that's going to do sampling, so you have some signal that you're going to measure and you're going to put it into A to D converter, analog to digital converter, so EEG, MEG, whatever source, sound, and you're going to record it and then digitize it so that you get MATLAB vectors instead of continuous signals. You want to pre-filter it. You want to put a device in front of it before you do the sampling that gets rid of the high frequencies you can't represent, or else they may masquerade as low frequency signals. Anybody here done some substantial amount of MRI? Anybody in MRI class and seen an MRI image where you get not only the image you expect of the brain, but you get kind of reflections of it on the image? Anybody seen that? So there can be artifacts in the MRI that basically lead to aliasing. And so, all these machines that do some kind of imaging or signal generation that's sampled generally we'll do something like what's happened here, which is to say, to throw away the highest frequencies that once I sample I can't represent, and that will masquerade as signals that aren't actually there. So get rid of the high frequencies that will alias the low frequencies. This is perfect timing to end. What we're going to do a week from today, I hope those who are leaving for SFN aren't going to miss me, is to apply this. And so we're going to apply it to auditory signals. So I'm going to talk a bit about, undergraduate level lecture on how the ear is built and what it does, and how the inner ear encodes things and what the neurons do. And then I'm going to talk about how people model what the inner ear is doing by building linear shift invariant systems that act like parts of the auditory system. And then I'll do a brief aside as to what all that has to do with music. So see you next week. Week from today.